Hey guys, I'm here back with another math video. Today we're going to be doing derivatives. It's a more derivative practice, and we're going to be practicing using derivatives to find the minimum and maximum value of a certain thing. So in this question, I'm going to ask you to try to find the maximum volume of a cone that can fit inside a sphere with radius 3, and try to use derivatives to solve it. And pause the video if you need to, and I'll give you the solution right now. So to solve this problem, we first know that the radius of the sphere is 3, of course, but we should try to first find a function for the volume of the cone in terms of a certain value. So let's say the value I want to use, the value that changes in my respect, would be the radius of the cone, which is r. Let's try to find the volume of the cone in terms of r. And to make this easier, let's actually draw a cross section of the circle. Let's say you had the cone in the sphere and you just cut a cross section out of that and cut it in half, so that what you were looking at would just be a side view of the of the figure. Let me try to make this as good as possible. Not perfect. And what we need is, first we know that the radius of the sphere is 3, and since all the these two corners of the cone, I should say, they're not exactly corners, these corners of the cone plus the top is touching the circle, which means that the center of the circle must have a line connecting these three corners per se, and the center of the circle would be right here, and these would all equal 3 because these are all radiuses of the sphere. And since the circle's radius is 3, and we know the cone's radius is r, here we can actually find this small bit of height right here, which, if you use Pythagorean's theorem, is just square root 9 minus r squared. Is that the length of that little bit right here? So the height of the cone would just be 9 minus r squared plus 3. This is the height of the cone because we just took a cross section of this figure and we looked at it from a side view, and that's sort of what you get. Now that we know the height of the cone, we can actually have a function for volume in terms of r. We know volume is, so the formula for the area of a cone, first of all, is pi r squared times height, that's the volume of a cylinder, multiplied by 1/3, that's the volume of a cone. And we know that height is equal to square root of 9 minus r squared plus 3, so this would be equal to pi r squared times square root of 9 minus r squared plus 3 times 1/3. We have a function for volume now, and let's take a look at what to do next. So in order to use a derivative to find the maximum and minimum value of a certain thing, let's just try to plot out an arbitrary graph so I can show you why the derivative tells you the maximum and minimum. Let's say we have r on this axis and volume on this axis, and the function looks sort of like this, which it doesn't actually. Let's say the function looked like that. As we can see here, well, actually I should make this a bit shorter. So you can see here, the maximum seems to be at this point and the minimum seems to be at this point. Now what the derivative tells us, remember, the derivative tells us the slope of the tangent line at a certain point. So for instance, at this point the slope would look something like this. Not that good. At this point it might look something like this. But what is the slope at the maximum and minimum values of this function? Well, if you draw it, it's just a flat line. The slope seems to be 0. And this is how we can find the maximum and minimum points, because the derivative will be equal to 0 at the maximum and minimum values of a function. So in order to solve for the maximum volume that the cone can possess in this problem, we should find the derivative of this volume function. And where that derivative equals 0 gives us the maximum value of v. I hope that makes sense. So finding the derivative of this v, first of all, we need to know the product rule of a derivative, which I don't think we have a video on yet, but I will prove it later. First of all, if you want to find the derivative of f of x multiplied by g of x, that is equal to f prime of x times g of x plus f of x g prime of x, which is just prime is just the derivative of that function. This is a rule you need to remember. It's very useful, and we'll probably do a proof video later on. Maybe next time I do a video when it's my turn. So you'll need that rule. So let's see what we have here. So our f of x will be 1/3 pi r squared, and our g of x will be 9 minus r squared plus 3. And so first of all, f prime of x, which is the derivative of this, if we attribute this as f of x, g of x, the derivative of f of x would be 2/3 pi r, because of the product rule. You multiply the power of r by its coefficient and then subtract 1 from the power, multiplied by just regular g of x, so square root 9 minus r squared plus 3, and add that onto just f of x, 1/3 pi r squared, multiplied by the derivative of g of x. And interesting thing about the derivative of g of x, you also need something called the chain rule. And yes, I like this problem because it incorporates a lot of derivative rules that I can just teach you guys in one sitting. So write down the product rule if you need it, because we're going to explain the chain rule now. And what the chain rule says is that if you have f of g of x and you want to find the derivative of that would be just g prime of x times f prime g of x. And let's try to use that in this equation. So to find the derivative of this function right here, find the derivative of that function, first we ignore 3 because 3 is a constant, it's just taken out. But the inside function, let's say g of x equals 9 minus r squared. G prime of x equals just negative 2r. Remember, because 9 just is cancelled out, and then multiply negative 1 by 2, so it's just negative 2r. That's g prime of x. Now f prime, let's say the f x equals square root of x, because g of x is getting square rooted in this function, and f prime of x is just 1/2 square root of x, because this is just equal to x to the 0.5, and you can use the product rule in that, which means this would be just g prime of x, which is negative 2x, multiplied by 1/2, and then you have to plug in g of x back in here, 1/2 square root 9 minus x squared. That took a good amount of our time, and this is our derivative for v prime. Now to find the maximum of this function, we'll have to find the values of where it is 0. So, let's just try to solve for this equal to 0, so this 0 equals this, and let's try to factor out some stuff. So first, let's well, what I can see from here is that every term seems to have, this is 2/3 pi r, this is 1/3 pi r squared. Every term seems to have 1/3 pi r in it, so we can factor that out. This just becomes 2 times 9 minus r squared plus 3. And then the second term would be, since 1/3 pi r squared is just this thing multiplied by r, that would be just r times negative 2, oh sorry, this is actually r, negative 2r times 1/2 9 minus r squared. Jeez, it's getting cramped. We'll have to erase the chain rule too. Sorry, I'm using paint, and they don't give you much room for this stuff. Okay, so let's see. Well, we already have one solution. If we factor out 1/3 pi r from this, we can see that r could equal 0. And if r is 0, the radius is 0, that would also give v prime a value of 0, and that slope would be 0. So I guess that's one solution. But another solution would be 2 times square root 9 minus r squared plus 3 plus, now we can cancel out 2 right here. Actually, that would actually be minus, because we have a minus sign in here. We have a minus sign right here, and then we can multiply the two r's together to get r squared. So that would be negative r squared over square root 9 minus r squared. Where do we go from here? Set this equal to 0. Well, one thing we can do that I think would work is that we can multiply everything by 9 minus r squared. That would cancel out some terms, because remember, if the right side is 0, then anything multiplied by 0 is just 0. So let's multiply by 9 minus r squared. So 2, and if you multiply 2, 9 minus r squared, 9 minus r squared plus 3, times, and if you multiply this by 9 minus r squared, that's just minus r squared. Okay, actually that's it's minus, plus, it's not times. So now we're left with this is equal to 0. And of course, if you multiply this out, you get 18 minus 2, 18 minus 2r squared plus 6, 9 minus r squared minus r squared. Okay. Actually, let's see if I can get more room. And where you go from here is would be 18 minus 3r squared plus 6, 9 minus r squared equals 0. What do we do from here? Well, we can divide everything by 3 to get 6 minus r squared plus 2 square root 9 minus r squared equals 0. And then what we can do from here is we can move r squared minus 6 to the right side. So that would be 2 square root 9 minus r squared equals r squared minus 6. And then we can square both sides. That would get us 4 times 9 minus r squared equals r4 minus 12 r squared plus 36. Okay, now we just simplify. In case you don't know, I'm running out of room, so I'll move down here. We move r squared to the, we move everything to the right side, so r4 minus 8r squared, and 36 cancels out spontaneously. That was totally not on purpose, actually wasn't. Equals 0, and then factor out r squared, so r squared minus 8 equals 0, and then you get r equals plus minus 2 root 2. That's really cool, but can the radius of a cone really be negative? I don't think so. So we're just left with r equals 2 root 2. So you have two solutions, which it got really messy, I'm really sorry. R equals 0 and r equals 2 root 2. So let's think about what happens if r is 0. If r is 0, this cone gets infinitely skinny, and that sort of makes it look like the volume is also 0. And remember, at minimums too, the slope can be 0. So remember, every time you have a solution for where the derivative is 0, it can either point to a minimum value or a maximum value. Maybe 2 root 2 is the maximum value. Maybe we could try that instead. So let's just try that out. Let me just keep drawing until I find some room. V equals pi 2 root 2 squared times height, which is going to be times height, which is this thing right here, times 1/3, and then I'm not going to solve it because I'm running out of room. And actually, if you solve this, you get 32 pi over 3. And that's sort of our solution. That is the maximum. And you can verify this because if you try other, usually if there's like a hump here, or a upside down hump, or like concave upwards or concave downwards, other terms you'll learn, that means that there's a possibility of the endpoints of the domain also being minimum and maximums, which means because like the slope, the tangent line here can't be 0 because like there's nothing to the right or left of this function, so you also have to test the endpoints because the endpoints can also be the solution. And here the endpoint was 0 because radius could be a minimum of 0, and the maximum was actually 3. And if you actually try 3 out, you don't get as high as a value as 32 pi over 2. Yeah, 32 pi over 2. 32 pi over 3 for the solution. So this is the maximum. It got really complicated. And, well, I hope you got everything, and I hope you sort of have a bit more experience with how to utilize derivatives in optimization problems. So I guess we'll see you next week. Bye. C. And you sort of have to predict that in order to prove it. So how do you prove these two triangles are similar? Because we'll use their similar relationship later to solve for A and B. Notice that angle B is already congruent to angle C. Whoops, angle C. So we already have one angle that's already proven to be the same. And, that's one of the steps that you need for similarity.